sorry he can't be here, but of course in Rechange we have Manin who arrived, and I'm very glad you're now here. You thought perhaps that this is planned that I talk about the Manin conjecture today, but that's purely coincidental. So what I'll do today is I'll start, we have made all kinds of preparations. I'm very grateful to Ching Li for doing a lot about UDNIM modules because that saves me a lot of time and energy. I'm grateful that the theory of displays has been completely discussed, so I can use that. And today we really start rolling up our sleeves and starting the proof. Now first I want to comment on the proof. If you have something like the Grothendieck conjecture, so what's the Grothendieck conjecture? You take a closed fiber, you take a Newton polygon lying below the Newton polygon with a closed fiber, and you want to construct a family which realizes this new Newton polygon. Now, of course, there's an obvious way to start. Namely, what you do, you take the closed fiber, you write out the full deformation theory, and now with your hands you feel all fibers in the deformation, what Newton polygons you've got, and if the Newton polygon you want is there, you're happy, and if it is not there, the conjecture is wrong. Now there's one little catch in this, namely these fibers are over this base, so are over non-perfect fields. And although the definition of a Newton polygon is quite straightforward, computing the Newton polygon is extremely difficult, especially over non-perfect fields. So if you take one of these fibers, they may be defined over some large transcendental extension in some formal completion and so on and so on. And there the p-divisible group is really difficult to describe, leave alone to describe this Newton polygon of all these fibers. So we've been struggling quite a long time to do the following: build a big machine, feed in the Grothendieck conjecture in front, and see what comes out. And nothing came out for a long, long period of time. And why, I've just explained to you. And I was working on this for a long time, and now in retrospect, I think I owe David Mumford an idea in a completely different situation, namely lifting a beam varieties to characteristic 0. And I'll explain it in 1 minute because that's very useful for the proof of today and tomorrow and Friday. You take the beam variety in characteristic P, you want to show it can be lifted. And there again you have a deformation theory, and you want to see whether it has a characteristic 0 fiber, and you get stuck. And then David Mumford came and said, well, what you have to do, you first take your beam variety in characteristic P, and you deform it in characteristic P to something you know which can be lifted. And ordinary beam varieties, these are just the theory of Z8 coordinates, and canonical lifts can be lifted. So you reduce your problem to a characteristic P problem of deforming your beam variety in characteristic P to an ordinary one. But that's a rather ad hoc thing. And Peter Norman and I finally carried out this Mumford program, and it's a difficult paper, and it's one of the most difficult computations I think I did, because there you really have to make a non-canonical choice of some deformation. And so it's completely not functorial, automatic, there's no big machine. Okay, so now in my proof here of the Grothendieck conjecture, there are 2 steps. And the second step is the machine. Trying, really proving the Grothendieck conjecture in a special case. And the magic word will be that the A number is at most 1. And now I'll explain that. So that's today. Today we do the nice case. And then tomorrow I'll show you how to go to the nice case. So if you want to have a picture of basically what we are doing in our proof is the following. Here is, say, the Newton polygon stratum to some gamma. And here's the Newton polygon strata of beta, and I'll soon explain. But this Newton polygon stratum may have a horrible singularity. Right? And now, suppose you have a point here, you can't see it in the back, and even not in the front. It's a very small point there, but it's in the singularity. Now, the deformation theory of this point is terrible. It's highly singular, obstructed, and how do you ever see it as a good thing? So, the proof consists of two things. First of all, you deform inside the regular locus of your Noether-Polygon stratum. So that will be tomorrow. So this is tomorrow. And now here, you know that this stratum is nice and smooth, and then you deform going outside, and that's today. And then on Friday I'll show you how to patch together things and draw conclusions. So today we have the easy case, deforming out of the smooth part. Tomorrow we have the more difficult part, moving from the singularity to the inside, and then just patching things together will really tell you everything. Okay, so before I move on, I will tell you one conjecture which I will prove today. Namely, please remember that we proved duality theory for being varieties. And from that you conclude that the Noether-Polygon is symmetric. So let me sketch you this proof. I have an Abelian variety. I take its Noether-Polygon, and I want to show it is symmetric. Symmetric means that the Noether-Polygon equals slopes beta 1 to beta h. They're rational numbers. And symmetric means that if you take 1 minus beta h up to 1 minus beta 1, so you take exactly the same slopes, but you subtract them from 1, then that you get exactly the same. And if these are ordered in a non-decreasing order, the same holds, of course, for these. So that's the definition of symmetric. Now, what is the proof? First of all, I proved for you that if you take the p-divisible group of the dual of a Abelian variety, then this is canonically isomorphic to the p-divisible group of your Abelian variety, Serre dual. And as I said, it looks innocent, but it is not completely obvious. Manin proved this in his thesis 1963 over a finite field, and later it was proved in quite generality. Then Ching Li discussed with you a p-divisible group GMN. That's a p-divisible group of dimension m, of height m plus n, and which is simple, and which is isoclinic of slope. And what you easily show, that if you take the Serre dual of this, well, what else can it be? I mean, the dual has dimension n, and the height is still this, so this you prove. And actually this is already over Fp. Now this one you prove easily if you use duality. You look into the thesis by Tadao Oda in 1966, and you will already find this material. And let me basically explain you why this is true. What is the Grothendieck module of this? This is a free W module on which F and V act. Now if you dualize, then you get a free Grothendieck module, the free W module, which is a Grothendieck module of its dual. And under duality, the F and M are interchanged. Now remember, this was given by an equation, V to the n minus F to the m, right? This is V to the n minus F to the n. And if V and F interchange, you just get the opposite thing. So morally, this is completely correct, and you just have to write out all the details of that proof. But it is easy, okay? And now you're done, because moreover, there is an isogeny from A to AT, right? And now this these three things of proof, well, of course, I prove the whole thing, because this says that the p-divisible group of A and the p-divisible group of AT is arginate, same Newton polygon on the one hand. On the other hand, you dualize the Newton polygon. That means you go to the dual p-divisible group, but a dual p-divisible group, as soon as the GMN appears here, the GNM appears here. So the GMN and the GNM appears the same multiplicity, and that's the proof. Okay, and now the conjecture. The Manin conjecture is the following. Suppose conversely, you do have a symmetric Newton polygon. You fix a prime number, which will be your characteristic. Does there exist a field in characteristic P such that there exists in the beam variety which is that Newton polygon? And I must tell you a little story. I was in Harvard 66, 67, and John Tate got a letter from Jean-Pierre Serre, and Tate showed it to me. And the letter said, well, I've proved the Manin conjecture, and he explained how to prove the Manin conjecture. But as I have not much news to tell you, I just end my letter here. And that was something people were really looking for a long time. Now, I hope to have time at the end of my talk to show you two proofs. One is by Tate theory, and I'll tell you how to do it. It's in the notes. And one is a corollary of the theory we are going to develop today. And you already see what's coming. We are really going to deform p-divisible groups. And if you know, a p-divisible group is a very small Newton polygon, so a very high up. And you have enough deformation theory, and if you would know the Grothendieck conjecture, then of course the Manin conjecture would follow. Because you can realize every Newton polygon in a family. So there it is. Yes? Okay. I like to start doing the things I have to do. And I will start giving you a definition. Everything is in the notes. But this is really important. So I want you to define the A number. Okay, so that's in 5.4. I have any group scheme in characteristic P, but let's do it for an beam variety, it doesn't matter. And this is over a field K. And I want to define you the number AK. AA. And for that I choose a perfect extension and I take alpha P. Remember, alpha P means alpha P over any base scheme, so here it is alpha P over L. I harm it into A, and this is of course over L now, sorry, AL. And I study this group. Of course, this group is a right module under the endomorphisms of alpha PL. And it's easily shown that this is isomorphic to your field L. I mean, you can multiply on the tangent space with any constant, and that defines you an endomorphism of your alpha P. So this is a right module under N that we usually call a vector space, and I can take the dimension, and that is the A number. So colloquially, A number is the number of alpha P's you can stick inside your beam variety. Please note that you have to go to the perfection. If you don't do, it may be that the dimension of K of alpha PA is different from the dimension of alpha PAL. There's a little slip in the lecture notes of Kizang Li and myself. We defined it without going to the perfection, but in the notes I've written a counterexample to that definition. Now, an easy remark, and that I could give you as an exercise, right? suppose K perfect, and to A you can associate the Grothendieck module of its p-divisible group. Right? And it might happen that a number of A is 1, and I claim this is the same as saying that if you take the local, how do we do that? If I take the local part of this and I take this, it's generated by one element. And of course the exercise is clear. If you take this module and you divide by the submodule generated by Fm and then by Vm, you get a vector space. You easily prove that that vector space is canonically this Hom. So that's what it proves. If that vector space is one-dimensional, then you have a non-commutative Nakayama to prove that your module is generated by one element. And I like to make another remark. You can discuss a finite group scheme over K, which is perfect, right? And this finite group scheme, say it is P power rank, is canonically isomorphic to its état local part, its local part, and its local étal part. So how do you find the étal and the local part? Well, that's just what Qingli did. You take the connected component of the identity, and the quotient is just the étal part, and then you can dualize, and on the Cartier dual you can do exactly the same thing. And so local means that the group scheme is a local group scheme, and also its dual is a local one. Now an example here is mu p, because that's état local. I should write my things better. État local, that's Z not p, and here is local étal, that's mu p, and this is alpha p. And if the base field is perfect, you have a direct sum. And the essence of Z8 coordinates is that for non-perfect fields, not necessarily so. And that's exactly that beautiful exercise Qingli gave you 2 days ago at the end, computing this X group, where Z mod P is in the co-kernel and mu P is in the kernel. And that X is non-zero for non-perfect fields, but for perfect fields it's split. Okay, so local means this, right? And the remark is that n local is non-zero if and only if Hom alpha p n is not zero. And the n local is just a tower of extensions of quotients alpha p if you work over an algebraically closed field. Okay, now the basic thing about the whole theory I'm going to tell you today is the following. If you have a p-divisible group over a base, mind everything is in characteristic P. So S is a scheme over spec Fp. And zeta is a Newton polygon, then we define script W zeta of S as a set of all points such that the Newton polygon is equal or lying above zeta. This sign means it's either equal or lying above. I mean, no points are below zeta, right? And the W open zeta of S, so this is a sign for open, is just the points where you have exactly equality. And Grothendieck proved that Newton polygons go up under specialization, and Nick Katz proved that theorem again by working out the proof by Grothendieck in much more precise form, namely saying that W zeta S in S is closed. And I discussed yesterday with you that this is not a representable functor and so on and so on. And if anyone has a good scheme structure a priori on these W's, I would be extremely happy, but it seems a hard problem. Okay, now let me make one remark, and that remark will be very essential tomorrow. How do you prove that this is closed? So let me spend hand waving and 1 minute on it. What you do is you take over your base something which you call the crystal of X. It's a kind of name mark that with a much better context which works over any base. And then you take exterior powers of your crystal, and then you take all Newton polygons of all these exterior powers. Now remember, what are you doing if you take a matrix and you take its first exterior power? What are the eigenvalues? They're just products of two eigenvalues of the preceding one. And the triple one is product of three eigenvalues, right? And then you can localize, you can find the points where the smallest eigenvalue of that operator jumps or doesn't jump. Now if you do all the exterior powers, you get all products, finite products of eigenvalues, and then you take the periodic values. So that's basically the proof of this. Right? So what you do, you take such an exterior power, you represent Frobenius or Verschiebung on that crystal, and you look at its smallest slope. How do you detect the smallest slope? By exactly describing periodic values of all the entries. So what are the defining equations of here? Defining equations are the following. You take all exterior powers of F on your crystal, and you put conditions on the smallest slope, so you put conditions on the periodic values of all the entries. So the number of equations is something like you take all entries in all exterior powers of Frobenius, and then you have a lot of equations on whether certain elements in beat vectors are zero or not. So the number of equations of this is enormous. And please remember that tomorrow, because tomorrow I will say exactly the opposite. So that's philosophically one very good point. Now I would comment on this thing a little bit. Namely, what I have defined for you, suppose, what do I want, zeta and beta? Doesn't matter so much. Let gamma be preceding beta, right? Then, from my definition, it's clear that if you take this, that this contains W gamma S. Right? Just by definition. Here you take all fibers which have Newton polygon beta or above. Of S certainly is in there, so it's in there, right? And you could also take the open part where beta exactly is realized, and you could take this Ritsky closure of this. Right? Now, this is closed, and this is closed, right? And this is the closure of this. So this certainly is, how do I say? So the question is W gamma S contained in W beta open S Zariski? You see, in defining this W zeta S, I could do two things. I could either take the definition as it stands, Or I could take the definition, take W zeta open and close it up. Do I get the same thing? And I'll give you an example where the answer is no in general. So that's a subtlety in the whole notation which you should pay attention to, but it doesn't matter so very much. Time is running fast. I want to make one more remark. In my whole theory today, I will discuss the non-polarized case. But there is also a generalization of the Grothendieck conjecture to a polarized version. If you have a polarized version, then automatically the Newton polygon is symmetric. And the generalized version indeed is correct for principal polarizations. So if the polarization is principal, the obvious way of asking Grothendieck conjecture does hold. But I'll give you an example that the generalization of Grothendieck conjecture for polarized abelian varieties and for polarized p-divisible groups is not true if the polarization is not principal. Now, I'll give you a counterexample to that. So there's a subtlety in the whole theory, but it gives you a lot of information how Newton polygon strata are nested in the moduli space. Okay, so now I really have to go to work, and I apologize for this blackboard. Apologies because this theory is not in the notes, and we should have incorporated it, but we didn't do it. It is in two papers which are cited in my notes, and it is certainly corollary of all the theory which was developed on this place. So let me go back in history. To my knowledge, David Mumford was the first who described this place. And what is a display and why do you like it? Or are you going to like it? You do Schlesinger deformation theory. So what do? You take some object, be p-divisible group, be a variety, or whatever, and you lift it to local Artin rings, and you keep lifting, and that defines your functor, gives you a representable functor, and so on and so on and so on. Now suppose you want to prove something. First of all, you want to prove that something is liftable. You do this lifting, and all of a sudden you get stuck somewhere at some level. Does it mean it's not liftable, or do you have to backtrack a few steps and then take another lifting? And that's very difficult. And that's one of the main difficulties of the whole deformation theory, first of all. Second of all, you know this functor is pro-representable, but how do you describe the generic fiber? How do you describe any properties of that? Abstractly, you really know a lot about it. For example, that beautiful theory which Ching Li told us, how the automorphism group of this closed fiber acts on that deformation space is beautiful, right? But to make explicit computation, to roll up your sleeves and really do a computation, that's hard. And for that purpose, Mumford found a beautiful way of doing it. So here's Mumford's idea worked out later in full generality and now proven in really the generality we would like to. This is a simple case. I take the JDNA module of a p-divisible group. That p-divisible group is arbitrary. And I think the field is perfect, but if you want to think of algebraically closed, that's okay. And I suppose the x0 is local. So that was the nilpotency condition which in Bill Messing's lecture showed up all the time. So this is far away from ordinary, right? You've thrown away the mu p part, you've thrown away the z mod, the qp mod zp part, you've thrown away all that, but you only are interested in the local part. And now Mumford's idea was to give an explicit matrix for Frobenius and deform that matrix. Now why does it work philosophically? If you deformed matrix still divides P, in the sense that that matrix multiplied something else is P. Then that matrix, if you tensor it up to the field of fractions and then to the perfection, gives you some matrix, and the Verschiebung you define by just dividing P by that matrix. So on that perfection, you get a matrix for Frobenius, you get a matrix for Verschiebung. So by the theory of p-divisible groups, you do get a p-divisible group over the perfection of the fraction field. And now the whole theory you have to prove is that that p-divisible group can be descended then first to the fraction field and then to this ring. And that's a lot of theory, and that's difficult. But the idea is completely obvious, right? So the theory of displays is you just take a matrix, you perturb the matrix to speak a non-pure mathematical language, and then you get a new matrix, and you claim that that matrix is the matrix of Frobenius of a p-divisible group over some ring. Okay, so here's the theory. You take a kind of hard theoretic filtration, yeah? You take a basis for Vm and you complete it to a basis for the whole module. And you describe your F on your basis. Now please mind that if I take F of one of these vectors, that's an image of V. So that's an F of an image of V. So it's F times V times something. So that's divisible by P. Right? And that's the reason why these matrices, well, they are in the V image, so that's what's written. So the display of Mumford is just, you write out F on this basis. A little remark on notation. The F of your p-divisible group, by covariant theory, becomes V on the module. And the V on your module becomes F, and the V on your p-divisible group becomes F. So I have the habit of writing script F on the module, which is a Frobenius, but which of course is MP of V. And this you should put in quotes, because this is a sigma linear map, and the V is a map from XP to X. So that's a morphism, and F is not a homomorphism, but it's of the linear module, but it's sigma linear. Okay, so you just write out a matrix of F on this basis. Now that seems a very nasty thing to do, but I'll assure you that this really gives everything you want. Okay, so first part of the theory, and the conclusion is here. I take any complete local ring in characteristic P with residue class field K, and I take elements in the maximal ideal, and I take the Teichmüller lifts of these elements to this Wheat ring. So these are just elements in the maximal ideal, and these are Teichmüller lifts. And we're going to apply it in two ways. One is that we choose a ring R and we choose Tij, and the other is that we take the Tij variables, and this will be the formal power series ring on all these variables, and the two cases are going to be used. This matrix is just rectangular. The size here is H, and the size here is C. But this is the best way to number these things. Now this F I write as a matrix A, C, B, P, where this just is block matrices according to this block and this block, right? So these are 4 block matrices. And if I do my homework correctly, you can really multiply T by C and by D and get this new matrix. Now what you have to prove, right, that this defines a display. So now you have a pair of two things. You have your ring R, and you have this matrix, which is later postulated to be the matrix of Frobenius. And now from this you have to go to this quadruple studied by Fink and discussed by Bill Messing in Langston. And of course the main point is that this really divides P, and that you have to do. And I'm not going to do that for you. Okay, so the claim is that R plus this matrix defines the display. Now, from the theory of displays, it says that a display corresponds to a p-divisible group over this formal spectrum, whose matrix is this. Let me make one remark which confused me for a long time. Here I write a formal spectrum, but sometimes people write a spectrum. And there's a paper by Johan de Jong, the references are exactly in the notes, which says that if you take a p-divisible group, which is a formal p-divisible group over a formal spectrum, then it comes from a p-divisible group over the spectrum of that ring. And this, of course, is not at all true for Abelian varieties. I mean, you're not saying that any complex analytic space is really algebraic, right? If you deform, if you take the full set 8 coordinates as described by Ching Li yesterday, of G squared full set 8 coordinates, the generic fiber of that is a formal abelian scheme over a formal ring, but certainly not algebraizable. But p-divisible groups always, quotation marks, algebraizable. But I just wrote the formal spectrum. Okay, now if you do this, the whole theory in my notes, and I'm certainly not, don't have time to really discuss all the details, is the following. Suppose you take these TIs and you take your Newton polygon picture, right? And you write your matrices in this way in your picture, right? Why not? I mean, I'm allowed to do that. And suppose you have just some Newton polygon gamma. Or did I call it beta? No, I want to call it beta. Okay, now the proof, which is completely in the notes, is the following. Suppose you take the following innocent thing. For beta, you define the parallelogram of beta. What is it? It's all the lattice points in my parallelogram. So this is the Newton polygon rho, the ordinary one. And I take all lattice points in this parallelogram which are on or above beta. So the ones here are forbidden, but the ones on the Newton polygon are okay, the one in the interior are okay, and the ones here are forbidden. Now, just do a mental exercise. You know the Feynman principle? The Feynman principle is you should have one example in mind, and if any formula is wrong in that example, then the whole theory is wrong. Okay, so here is the example. You know that if you take rho, right, what is the deformation space of all deformations? It is just D times C. It is just the dimension times the dimension of the dual, right? And that we'll use tomorrow, and that has been proved by Ching Li, and it's proved in the notes. And so the exercise is just take all lattice points which are on rho or above rho, but not on this. Prove that these are exactly D times C, but that's obvious, right? So now the theorem says, take this parallelogram of beta, so all the points in this, all the lattice points in this region, possibly on the Newton polygon, but not on the thing above. Then I can form the following ring. I take R beta, I take all lattice points in this parallelogram, I take formal variables, and I formally adjoin them to my base field. This is a formal power series ring on how many variables. The number of variables is exactly the lattice points in beta, in triangle of beta, in the parallelogram of beta, and this I baptized the dimension of beta. So the dimension of beta is just a purely combinatorial, easy object. So this is obvious, right? It's just notation. And now comes the theorem. The theorem says that if I start with a closed fiber where the A number is at most 1, then I can take the beta Newton polygon stratum in this deformation space, and that is, well, it's canonically isomorphic to the formal spectrum of beta. So if you accept this theorem, I really prove for you what I said before, namely that as soon as the A number is at most 1, all the Newton polygon strata containing that point, locally at that point, are really regular, really smooth over your base field. And they're nested exactly like they do. I mean, if you go up with your Newton polygon by deleting this point but taking a little bit higher, the codimension is 1, and the defining equation is just given by this variable, and so on and so on and so on. Right? So this really proves proves the dimension formula. Okay, now I'm not going to give you the proof of this, but the proof is in the notes and is really very easy. Namely, the proof in the notes is as follows. So I'll spend 2 minutes on it and then I move on to more interesting things. If this DNA module is generated by one element, I can normalize my coordinates in a very obvious way. Namely, I can take this for the generator, then E2, the Frobenius of that generator, for E3, the Frobenius squared, and so on. And then this matrix really simplifies a lot. Now you all know the Cayley-Hamilton theorem. The Cayley-Hamilton theorem says that if you take a matrix over a commutative ring, mind commutative, you take its characteristic polynomial, that's a polynomial over your base ring, and you substitute formally in the variable your matrix, you get a square matrix, right? And the Cayley-Hamilton theorem says that this is 0. Now in the proof, in the notes I've given 2 proofs, and if you ever teach a class in linear algebra, these proofs are really fantastic. One uses heuristic topology and one uses very easy things. And if you notice a heuristic topology proof, the other proof is much more digestible. So the Cayley-Hamilton theorem is really quite okay. Now, what I would like to have is a Cayley-Hamilton theorem in this case. Namely, Frobenius operates in a certain way on E1 in this matrix form. Right? And you can see how it works. I mean, this matrix is completely explicit. This is subdiagonal, and then there are all kinds of entries elsewhere. Right? And then you can try to compute whether F satisfies a certain Cayley-Hamilton equation. That is, if there's a linear combination of the F power I, which annihilates the first element. And if you believe Cayley-Hamilton over a non-commutative ring, this is obvious. What you have to do, you just write out the characteristic polynomial, and you substitute F in there. Now, of course, there's a little catch, which is a big catch. Namely, F is only sigma linear on the coefficient. So you have to say whether F is on the right-hand side of all your variables or coefficients, or on the left-hand side. First of all. Second of all, if I take, instead of E1, I take a multiple of E1, and I take some combination of powers of F which annihilates E1, there's no reason it annihilates that multiple. Because that multiple, that lambda which you put in front, to all powers of f gets raised to the lambda to the power sigma to the I, and you get a complete mess. Okay, so now the claim is there does exist, under the condition that the A number is 1, there does exist a polynomial of degree h in f, which coefficients in W are, which really annihilates the first element. So the new Jordan module is something like the Jordan ring modulo this relation. And now you're happy, because now you exactly know how to compute the Newton polygon of that. I mean, that's just factoring this polynomial over some extension and so on and so on. Okay, so that works for A number 1, and that proves the theorem. Now, I'm not going to spell out the details, because that would really take a long time. And instead, I want to give you one example and to prove the Manin conjecture. Okay. So, just a few words on quotation mark the old proof, the proof which Serre had in mind and which was completely worked out by Tate in of proving the Manin conjecture. So I just quote from, where is it? 315 and 313. So in the notes you have to go back to 315 and 15. The following: you take integers which are relatively prime, and I want to prove the Manin conjecture for the Newton polygon given by these pairs. So here the height is 2G, where G is m plus n, and this is a symmetric Newton polygon, and we want to prove it for this. Suppose we have done this, then of course you're okay, because any Newton polygon can be which is symmetric can be written as such pairs plus the 1-1s. But the 1-1 is the Newton polygon of a supersingular elliptic curve. So then the abelian variety you're looking for is just realized by a product of such abelian varieties and supersingular elliptic curves. Okay, so you want to do this, and what you do, you write down a polynomial. You take t squared. You take p to the n t, where n is the smallest, mind, plus p to the power g, where g is the sum of the smallest and the biggest, and p to the g we baptize q, right? And now it's obvious that that 0 of this polynomial is complex. Yeah, of course, because the discriminant is b squared minus 4c is p2n minus 4p to the g, but mine g is m plus n. So pn squared is smaller than, even smaller than pg squared. So this is complex. Okay, now you know that pi conjugate in the complex numbers, that this is q. Yeah? So you have constructed a very q number. And now Honda Tate implies, so that's 313, that there does exist a beam variety over FQ such that the Frobenius of this is conjugate to pi. Yeah? So what is the Frobenius? The Frobenius of A is just F times F G times. And this is a bad notation. It is A mapping to AP, and then AP mapping to AP squared. So here I should write F, then F A, this is FAP, and so on. Right? Now this is an anamorphism. It sits in the beam variety, so it's an algebraic number, and that number is conjugate to this. So that's the theorem by Honda and Tate, right? That's the difficult part. And now comes the easy part, and I give you that as an exercise. Show that the neutral polygon of this A is the psi, which is Mn plus Nm. And mind that you know exactly what the p-adic value of A are, and A is just a Frobenius, the geometric Frobenius on your beam variety, and you just move on, right? And you know, Qingli has explained to you how the GMN and the GNM, how Frobenius operates there, so you just do it, right? So this is the proof of the Manin conjecture, 1967, by Serre and by Honda and by Tate. Now we give a complete new proof, which you find in, what is it, in 519. And the trick is, you start with the following fact. Given P and G, there does exist a beam variety such that the neutral polygon of B0 is sigma, it as supersingular, and the A number of B0 equals 1. Now, I indicate in the notes two proofs. One proof is a reference to the lecture notes of Kees-Ing Lee and myself. We prove that, in fact, any generic point of any component of the supersingular locus has A number 1. But on Friday, I will prove this fact again for you using deformations of filtered p-divisible groups and so on and so on. Okay, so there are two proofs at least for this, and you're done. Okay, but now I'm very happy, because what I do is I take the deformation space of B0, right? And you know exactly which neutral polygons appear here. Namely, you take the picture which we had before, right? You take the parallelogram and you take all the deformation space. So what you do is, here is my sigma, right? Here is my deformation space, and here's my what I want, xi, right? Now the polarized version is slightly different. The polarized version says that your matrix is symmetric, and you really have to take all points on this. So now I take the triangle of xi, which is exactly the points x, y in the parallelogram of xi, such moreover that the x coordinate is at mode G. And the symmetry conditions, and B is principally polarized. And it's a principal polarization on B0. That's very important. Okay, now a variant of the theorem which I have there which are completely written out in my notes, is that in this deformation space, the locus which you get by W psi is exactly given as is before in such a deformation ring, and actually it is exactly the dimension of the number of integral points indicated here, and all these Newton-Polygon strata are nested exactly as Newton polygons are nested by inclusion. Okay, so that proves that I take W psi open, that this is non-empty, because all Newton polygons above are lower dimensional and a finite number, so I throw out a finite number of lower dimensional subspace and I still get something. And this gives another proof of the Manin conjecture. Now let me make two comments. First of all, it looks like that this proof, so this is the first proof, that this proof is really nice. But mind that we really use a big black box, namely Honda-Tate theory. How do you prove Honda-Tate theory? The Honda-Tate theory, there's a lot of things which are rather elementary and algebraic and so on and so on and so on. But there's one difficult theorem. The difficult theorem says that if you take your Wayne number, then you can extend your field, your finite field, and you don't know how much. You can take an isogeny, and you don't know how much, and that one can be CM lifted to characteristic 0. So the proof is that you take a CM abelian variety in characteristic 0, which you hope has the correct mod P Newton polygon, and then you have to prove that that really reduces well, and so on and so on and so on. So that's characteristic 0 construction and the whole reduction mod P, and exactly following what the Newton polygon is going to be, goes into the Honda-Tate theory, and that's a rather difficult thing, right? And here we have a completely elementary proof once you know the theory of displays. So this is a completely different thing, and there's no characteristic 0 involved here. Let's give you the second proof. I have luckily 2 more minutes, and I'll give you an example. And the example is, let me take G arbitrary, but to be simple, let's do G is 3. But any bigger G also would work. And let's take P to the power 1 plus 2. And if this G is arbitrary, then I take 1 plus 2 plus 3 plus up to G minus 1. So this is P cubed, but the 3 is 1 plus 2. Right? And I consider A, the modular space, of dimension G with polarization of degree D squared. And I take of this the supersingular locus. And my claim is that this supersingular locus contains an irreducible component of dimension equal to 3. Yes? Let's suppose I have done this. Then it follows, but you can also compute, that if I take T generic, that the A number of my generic fiber is 1, and that follows from the construction I'm going to give you, but it also follows from the paper with Norman, right? Then, now you have a strange thing. Let psi be 2, 1 plus 1, 2. Yeah? So that's the Newton polygons of slope 1/3 and 2/3 length 3, right? So this is my Newton polygon, and this is my other Newton polygon. So this slope 1/3 and this slope 2/3. Okay, now I have the following claims. Let this A eta be baptized B0 and go to some perfect field if you like. There is no B over some S integral such that B 0 is an, and the Newton polygon of B generic is psi. Now why is this? You see, you know that if I take W psi of AG any D, where psi is this one, that the dimension of every component of this one is 3. And that follows from the paper by Norman and myself. So this is a 3-dimensional locus. And this 3-dimensional locus certainly does not contain T. So the generic point of T is outside this locus. So there's no way of deforming this point to a generic fiber where the Newton polygon is psi. Right? But mind the following strange fact. There does exist a p-divisible group over some y, such and a point 0 yk, such that if you take y0, that this is isomorphic to b0 p infinity, and the Newton polygon of b generic, of y generic, is psi. Why is that? Well, that you know, because the central fiber has a number 1, and today we've proved the Grothendieck conjecture for central fibers with a number 1. So you can deform y0. Yeah? So let me finish there. So this shows that if you take W psi open AGD, in the case we have here, and you close it up, it does not contain W sigma AGD. Yeah? Okay. Well, thank you very much for your attention, and next tomorrow we'll go.